Hello, welcome to yet another how-to video on RA microcontrollers. We are looking at one of the most common connectors today, the USB. RA microcontrollers support native USB connectivity, that is, we can use the pins on the MCU chip to form a communication channel to USB connectors and directly connect to the PC via a USB cable. For this demonstration, we are going to use two micro USB to USB-A cable. One cable will be used for debugging and another cable will be used for the USB communications. In terms of the connection port, we are utilizing the J10 and J11 micro USB ports on the EK board. So, the steps to connect the cables would go like this. Connect the micro USB end of the cable to the micro AB USB debug USB port, labeled J10 on the EK RA6M4 board. Next, take the opposite end of the cable and plug it into a USB port on your host PC. Check the EK RA6M4 board. The power LED labeled LED4 should light up white, indicating that the board is successfully powered. Now, let's connect another USB cable. Plug the micro USB end of the device cable into the micro AB USB full speed port labeled J11 on the EK RA6M4 board. Then, connect the other end of the cable to a USB port on your host PC. Next, let's place jumper J12. Ensure that jumper J12 is connected to pins 2 and 3. Finally, connect the jumper pins for J15. Take note that the USB cable on J10 is supplying power to the board, so it is essential to keep it connected while running the demonstration project. Now, we shall proceed to developing the demo application in E2 Studio. As usual, we will create and launch a new RA C++ project. We shall select the target board to be EK RA6M4. For the rest of the options, we shall use the defaults and finish with the minimal project selection. The project contents will be initialized. We need only one stack for this project, and that is the USB PCDC or USB Peripheral Communications Device Class driver. Once added to the project, we will notice a warning. It seems like the USB clock or UCLK needs to be configured at 48 MHz. So, we navigate to the Clocks tab. There are several ways to obtain a 48 MHz for the clock. First, we need to enable the UCLK and then select PLL as the clock source. Next, we need to configure some multiplying and division factors to produce the desired frequency. We shall make the division factor to 4 and then one of the multipliers to be x24. That would produce the frequency for 48 MHz for the USB clock. And the error is gone. There is nothing further to change in the USB stack, so we can proceed to generating the project contents. Once done, we shall navigate to the hullentry.c file. The USB is a versatile communication method, so it's quite some coding involved to write a basic driver. Let's hop on. We start by including the standard I/O library and the string library. Then we are going to define the macro for the number of USB descriptors. USB descriptors are structures that hold information about the USB module. So, we are going to declare some external variables or more specifically arrays, which will be used to store the values for the USB driver. We need to add an additional file called RPCDC descriptor, which contains the definitions of these structures. Coming back to our hull entry file, we can see that these external variables are still not initialized, which means we are not yet using them in our program. Before we make use of these descriptor variables, we are going to define another macro for line coding parameter and also initialize a variable BUSBAttach to false. This variable will be checked later to ensure USB connectivity is active. Then we are going to define our USB descriptor, which is a data of type USB descriptor proprietary to Renesas. It is in this structure that we will embed the previously declared variables for USB descriptor. We shall include the number of descriptors here. And then we shall write the text that we want to send to the PC terminal through the USB. A function to check for write complete operations of the USB port is implemented. We start with initializing the USB status variable, a custom data defined for FSP. Then we shall have a variable for the timeout value, a variable for the FSP API implementation status, and another variable for USB information of data type USB event info T. Then we will define a do-while loop. This loop will basically run until the USB write operation has been completed or the timer has run out. So we start by calling the USB get event API, which takes two arguments. These are the pointers to the variables USB event info and USB event status. And then we will add a small error handling for unsuccessful API calls. Now we shall also add the decrement operation for the timeout counter in each loop. This will be followed by putting a break statement and FSP status reset in the exceeded timeout condition. We shall end the do-while loop by adding the normal break condition, which is not until the USB write event is completed. And then we shall end the write complete operations function by returning the FSP status variable. The next function is to print a text on the PC console and name it print to console. As usual, we shall declare a local FSP error status variable. Then another variable is declared to hold the length of the data to be transferred. And then we will add the USB write API, which will send data to the PC terminal. As destination, we will use the macro USB class PCDC. This will be followed by an error handling. Now, once the API has been called, we shall execute the function we just defined before this, the check for write complete function. This function should ideally return an FSP success status. In cases where the USB write fails and we don't get an FSP success status, we shall then set an error status to USB write fail and assign that as the return value for the current function. Before we move on to the hull entry function, we shall declare a global USB event variable. In the hull entry function, we shall declare and initialize these local variables: an FSP status variable, a USB event info variable, a USB PCDC line coding variable, and an integer array for buffer. Then we are going to call the Open USB Channel API from Developer's Assistance. An assert macro is used to ensure the Open USB call is executed successfully. Then we are going to make the while loop. We shall cover the rest of the program in the next part.